I'm going to now introduce to you the concept of Ksp, which is simply another equilibrium problem. You can treat it as an equilibrium problem if you want, but I'm going to show you some tricks of the trade. So Ksp is another K calculation. It is the solubility product constant. So let's review all the Ks that we've learned. We've learned Kw, which is the water dissociation constant, Ka, which is the acid dissociation constant, Kb is the base dissociation constant, Keq is the equilibrium dissociation constant. So what this refers to is slightly soluble salts. Examples, I'm going to do an example of each type. Barium sulfate is not very soluble. It's going to say it's a solid, but even the least soluble salt dissolves just a little bit into just a few barium ions and sulfate ions. So we're going to do an ice chart. And remember, solids don't play this game. So every single time, it's still going to be products over the reactants, but the reactants are always solids. So in any ice chart, the initial is 0 for the products. We'll get one piece of barium and one piece of sulfate when they dissolve, like such. So I'm going to teach you a trick where we don't have to do the ice chart every single time. So remember, Ks are always products over the reactants. So it's the concentration of the products raised to their coefficients over the concentration of reactants, which are always solids, so will always be ignored. So every single time you have two ions, you will have the same thing. Ksp will equal x squared. Let's do the same thing for 3-ion salt. Calcium fluoride is very slightly soluble, but we'll get a couple pieces. For this, you're going to get 1 calcium and 2 fluorines. So pay close attention to this ice chart. No solids, zeros. There will be cases where those aren't zeros. Those are called common ion problems, but for straight Ksp, those are zeros. Now this becomes plus x, and this becomes plus 2x. So let's go ahead and plug that into Ksp is equal to concentration of calcium times the concentration of fluoride squared. So I'll plug these in there. He's x. He is 2x squared. So anytime you have 3 ions, doesn't matter the combination, you're dealing with 4x cubed every single time there is 3 ions. Let's do 4 ions. So you'll get 1 aluminum and 3 hydroxide. It's never going to be 2 and 2, because in ionic compounds, if you had 2 cations and 2 anions, they would reduce down. So I'm going to run through the ice chart quick. And hopefully you guys will get real quick where you don't have to do the ice chart. Now let's carefully plug this in. Ksp is equal to aluminum times hydroxide cubed. So x and 3x cubed. It's not 9 though, is it? What is it? 27x to the 4th. Anytime you have 4 ions, it will be 27x to the 4th. X is going to be what we call the solubility of the salt. Because one piece of this guy, or X pieces, is going to dissolve, and for every X pieces, you get a particular amount of ions. And the last one, 5 ions. Doesn't matter if you have 3 cations and 2 anions, or if you have opposite 2 cations and 3 anions, doesn't matter. So he's going to dissolve a little bit into 3 SRs and 2 phosphate ions. I'm going to do the ice chart for each of these, and we'll get 3 cations and 2 anions for every 1 or X pieces that we dissolve. Like such. So now let's plug that in. Ksp to the 3rd phosphate squared. Plug them in. 3x to the 3rd and 2x squared. You see it yet? That's every time you have 5 ions. This problem you'll solve is 108 x to the 5th. So let's summarize that. So 2 ions, Ksp is equal to x squared. 3 ions, Ksp is equal to 4x to the 3rd. 4 ions, Ksp is equal to 27x to the 4th. And our last one that's even slightly reasonable would be 5 ions. Ksp is 108x to the 5th. Let's look at our patterns here. So don't forget, this is the mistake I see people making, is they'll either say 9x cubed, or they'll just be like, oh, 3x to the 3rd, and they forget to cube it all together. So Ksp is the solubility product constant. When we solve for x, so Ksp is a value we can look up. The Ksp for barium sulfate is 1.1 times 10 to the minus 10. So you can solve for x by taking the square root. The square root of x, sometimes you're going to see it written as s. If you see 4x or 4s squared, it's the same thing, x and s, because s stands for the solubility. That's how many pieces of our salt will dissolve. And in this case, it dissolves into two pieces. So we can take the square root of 1.1 times 10 to the minus 10 and get a solubility of 1.0 times 10 to the minus fifth. That's how many moles will dissolve. So it can be in molarity, it can be, there's lots of different units that are possible for solubility, but we'll leave it as molarity for today. Let's do calcium fluoride. So Ksp is a value we can look up, it's a constant. It's 3.9 times 10 to the minus 11. So to solve for x, I take 3.9 times 10 to the minus 11, divide it by 4, and then I take the cubed root. So in your calculator, you guys have fancy calculators. If you're doing a simple calculator, you can raise it to the 1/3 power. There's lots of different tricks, but if you need help with that. So X is going to represent the solubility of calcium fluoride, because notice for every one piece that you dissolve, you get one piece of calcium, two pieces of fluorine. So that X value plays double duty there. So I get 2.1 times 10 to the minus 4 is the solubility. That's how many moles will dissolve per liter. Aluminum hydroxide has a Ksp value of 4.0 times 10 to the minus 15. Notice I cannot make assumptions about the solubility based on the Ksp, because each one of them is going to go through a different process to calculate. So I'm going to do 4 times 10 to the minus 15 divided by 27 first, and then I'm going to take the fourth root, and I get 1.1 times 10 to the minus 4. So this is the value of X that you would compare if you were to say which one is the most soluble, not the Ksps. The Ksps don't give you that information directly. Ksp here is 1.0 times 10 to the minus 31. But it has to go through lots of manipulations to get that tiny, tiny number. So we won't make assumptions. We're going to solve for X by first dividing by 108 and then raising it to the 1/5 power, or taking the fifth root of it, whatever works in your calculator. And I get 2.5 times 10 to the minus 7. That's what you're going to solve for when they ask you for the solubility. So let's add that to the summary. If you are asked to find the Ksp, they'll probably give you the solubility. If you're asked to find S, that's going to be the solubility. That's going to be your value of X or S, depending on which variable they decided to call it.